Hello, in this video we're going to look at optimization. Optimization is just an applied use of derivatives where you're using the first derivative to identify the max or the min in some sort of word problem. What's the maximum profit? What's the minimum cost? Those sorts of questions. How high does the football go? And you're going to use the fact that the first derivative gives you critical points when the first derivative equals zero. To identify those candidates that could be the max or the min. We're going to start out with kind of a simple example. We're going to have two numbers which add to 20. Let me show you in the book the example which I'm going to use. So we're looking at just question number 1 here. It says finding numbers. The sum of two non-negative numbers is 20. So right off the bat, that means that if we call the numbers x plus y, then they add up to 20. They're non-negative, which means you can't have -2. You can't have, -3 plus 23 makes 20. So they're only positive numbers. It says find numbers to where the sum of their squares is as large as possible and also as small as possible. So we're going to take the sum of their squares. I'm going to say total equals x squared plus y squared. That's the sum of their squares. And I want to know what's the max or min. So this is my setup. For starters, the total is written as a function of two independent variables, x and y. That is a bad setup. You want to have one independent variable, if at all possible. So up here we have a relationship between the two variables, x plus y equals 20. How are they related to each other? So I'm just going to take the liberty of saying y equals 20 minus x. That means the same thing. We're going to substitute that in here so I can knock this down to a single independent variable. Total as a function of x squared plus y squared, except y is now 20 minus x. We're going to identify critical points by taking the first derivative and seeing where that equals 0. Take the outside derivative for this chain rule, recopy the inside, multiply by the inside derivative, set that equal to 0. What do we have here? 2x plus 40 minus 2x. Sorry, all that is times -1, isn't it? So 40 minus 2x times -1 equals 0. One more time, 2x, 40 times -1 is minus 40. Minus 2x times -1 is so that. So we've got 2x and 2x is 4x. Minus 40 equals 0. So x equals 10. This is a critical point right here. X equals 10. You have to also remember that we have endpoints. You don't always have endpoints, but endpoints can be maxes or mins as well. Because these add up to 20 and they're not negative, the endpoints would be 0 for x or 20. So we've got to consider all three of those points to determine where my maxes or mins happen to lie. And we'll check it on the calculator after we're done. So x, y, x squared plus y squared. So I've got 10 with my critical point, 0 and 20 are my endpoints. If these add to 20, if x is 0, then y is 20. If x is 10, then y is 10. If x is 20, then y is 0. Let's look at the x squared plus y squared. This first one is 0 plus 20, 400. 10 squared and 10 squared, 100 plus 100 is 200. And 20 squared is 400 plus 0 is 400. These are maxes. They're local maxes. They're not global maxes, but then we have a min right there. Let's look at this on the calculator and just kind of confirm what we did algebraically. Y equals, I'm going to type in my t of x squared plus 20 minus x squared I'm going to do zoom standard to see what we're dealing with here. Also, my window's no good here because look, the x can go from 0 to 20. First of all, I've got negative 10 to 10. That's no good. And my y, my total could be like 400 or 200. So clearly I need to change my window. X will go from 0 to 20. And y can go from like 0 to like, how about 450? We'll count, what am I doing? 450. Count by 50s. So this will be a more sensible window. Okay, so if you go to trace at x is 0, whoops. Let's go back. It changed my window on me. 0, 20, and I had 0 and 450. Let's look at that one more time. Okay, there's my graph again. Let's trace and look at 0, 10, and 20. Those are my 3 x values of interest. So at 0, you can see my x squared plus y squared is 400. It's right there. It's a max. At 10, when x is 10 and y is 10, they're squared. The sum is a minimum. And then you can see back here on the right side, we go back up to 400. So that looks like a reasonable outcome. Don't ever forget about endpoints. If there's endpoints, they definitely need to, they're part of the game. Let's try another problem. So imagine you have a barnyard. And so here's your barn. And you have 700 feet of fence, and you need 3 pins. So this is a barn. So your fence is going to look like this. And you need 3 pins. And we're going to see what the maximum area is you can make with these 3 pins. You don't need fence on the barn because it's a barn, but you need fence around the outside and then 2 dividers for the inside. So we're going to use optimization to work this out. I'm going to call this x, and this x, and this x. And this is going to be y, and thus this side is y also. So first we need an equation that relates my independent variables, x's and y's. We've got 2 y's, we've got 3 x's, and those are going to be 700. Then my total area is going to be y times x, the whole, that side times the whole this side. So x times y is my total area. This is what I want to maximize. So you need, if there's more than one variable, you need an equation that describes the relationship between those 2 independent variables. Then you need what it is you want to maximize, and that is this. So I'm going to say, if you want to solve, say for y here again, subtract 3x, get y as 700 minus 3x over 2. And so I'm going to say we've got x times 350 minus 1.5x. That's the area as a function of x equation. So 350x minus 1.5x squared. And the derivative of that now, we're going to take that, set it equal to 0, find my critical points. A prime is going to be 350 minus 3x equals 0. And my critical point is going to be x is 350 over 3. Also endpoints. Now this is kind of the endpoints here are kind of trivial. X could be 0 and y could be, you could have an x of 0, and this would just be, it wouldn't be a pin, it would just be basically a line. and then x could be y could be 0, and you just have like a fence along the barn. The reason those are trivial is they lead to an area of 0. So those obviously would be mins, but they're trivial min because we're realistic here. We need a barnyard, so you can't have an area of 0 that would be functional. But keep in mind the endpoints. X is 0 or y is 0. In theory, you should consider those, but I know that they're not going to be useful in this context. So keep the context of the problem in question in mind. So if x is 350 over 3, that means that 3 of those are going to use up 350 feet. We would have then an additional 350 feet to divide between two y's. So y would be 175 in feet, and you'd have basically your barn would be right here. You'd have 175, 175, and then you'd have 350 over 3. That's going to be, I'm just going to call it that. It's like 100, almost 117 feet, but not quite. So that's what your barnyard is going to look like. And you could graph this again and verify that it's going to be a max. But you really don't need to, because I can just look at this and see, oh, that's a parabola. It's got a negative number in front of a square term, so it's going to look like that. It's going to be an upside down parabola. So obviously the only critical point must be a max. So I can just, by kind of general knowledge of quadratic equations, I can see that must be a max because it's an upside down parabola. So this is, and then 175 times 350 over 3, whatever that number is, that is the total area. That would be the maximum area you could have. Okay. Let's just do a kind of a basic cost profit type question. Those are pretty common. Let me move this over. Okay, I'm looking at question 23. It says, suppose the revenue function is 8 roots of x and the cost is 2x squared. X is measured in thousands of units that are sold. What production level maximizes profit? So you got to remember, profit is revenue minus cost. And so in our case, profit as a function of x is going to be 8 roots of x minus 2x squared. So to take the first derivative and then find the critical points, this is going to be x to the 1/2, by the way. You'll have 4 x to the negative 1/2. The 1/2 comes down, multiplies by 8, you get 4. Drop the power from 1/2 down to negative 1/2. Then that, we're going to set it equal to 0. Let's do some algebra first. 4 over root x minus 4x over 1 equals 0. I'm going to start there. And I guess I need a common denominator here. So the root x would be a good option. So you're going to have 4 over root x minus, if I multiply x to the 1 times x to the 1/2, we're going to have 4 x to the 3/2 over that. And I'm just going to rewrite this as root x when does that equal 0? So something to know, first of all, obviously you can't have a 0 under the square root. That would be, you can't have a 0 in the bottom of the fraction, so x cannot be 0. Also, you can't have a negative under the square root, so x cannot be negative. Because x is the number of 1,000 items sold, obviously you can't have negative items sold anyway, so that's not a concern. Also, we're going to just say we're ruling out the case where we sell 0 items, because that's probably not a very useful case to consider anyway. So keeping in mind that x is a positive number, I don't care what the bottom is. In order to make this 0, we just need to say when is 4 minus 4x to the 3 halves equals 0. You can divide by 4 and say when is this true? Or otherwise, when is x to the 3 halves equal to 1? And it's at 1. That's the critical point here. So if that's the critical point, we know it's going to be a max or a min. We don't have any other critical points. So let's do two things here. Let's make a number line. X p prime. Here's 1. This is a critical point right here. I want to look at the sign of the derivative on the right and left to determine if this is a max or a min. So perhaps I go back up here and I plug in. Let's pick an easy number to work with. How about we pick with, and here's my derivative right here. Let's pick x equals 4 maybe, because that's got a nice easy derivative. The square root of 4 that's 2 on the bottom. 4 minus 4 to the 3 halves power is 8. So 4 minus 32. That's a negative over there on the right side. That's a critical point right there. Can't really see it very well. Critical point. If I picked a number below 1, oh man, how about we pick like a quarter, because that's another number we can take a square root of. Zeros down here perhaps. So a quarter on the bottom is square root of that's a half, that's positive. A quarter here, if you take the 3 halves power and a quarter, it's an eighth. 4 minus an eighth times 4, that's 4 minus 1 half, it's positive. So here we're going up, then we're going down. That appears to be a max. That's a max because we go up with a positive slope and then down with a negative slope. That means that at x equals 1, or 1,000 units, we have a max. And let's verify that now with my calculator. I'm going to graph the original function, which is, here we go, 8 root x minus 2x squared. I'll go to zoom standard.